For more than 4 light years, Alpha Centauri has sat in our sky like a promise, the nearest star system containing suns like ours, close enough that it feels almost like a neighbor. For generations, astronomers assumed that what was closest must be best understood. Then James Webb looked directly at it, and the result was not reassurance. It was a planet that appeared once, clearly, and then vanished. A system that our most powerful observatory in history had to build a custom observing sequence just to study. A nearby sun-like stellar neighbor that turns out to be harder to interpret than galaxies billions of light years away. This is the story of the moment proximity stopped feeling like clarity, and the universe's most familiar stellar address became something far stranger. This small team spent serious hours digging into the actual papers and mission updates behind this story. So if it sparked something for you, a like tells the algorithm this work was worth making, and a subscribe keeps us going. In 3, 2, 1, liftoff. There is a star system that almost every person who has ever looked up at a clear southern sky has seen without knowing it. It sits near the Southern Cross, burning with a combined light bright enough to make it one of the most luminous points visible from Earth. To the naked eye, it looks like a single star, dazzling and close, a steady warm point of light that ancient peoples of the Southern Hemisphere wove into their navigational knowledge and their stories about the sky. But it is not a single star. It is a system of 3, 2 of them remarkably similar to our own sun. The third a small, dim red dwarf orbiting far out in the dark. We call it Alpha Centauri. And for as long as humanity has had the tools to measure the distances between stars, we have known one central, staggering fact about it. It is the nearest stellar system to our own, 4.37 light years away. A distance so close on the cosmic scale that it has felt, for generations, like something we already understood. That feeling of understanding is what this story is about. And it is the first thing we need to carefully take apart. Alpha Centauri sits in the constellation Centaurus. The 2 main stars of the system, Alpha Centauri A and Alpha Centauri B, are so close to each other in physical terms that they orbit their shared center of mass once roughly every 80 years. They are separated by an average distance of about 23 times the distance between Earth and the Sun, which sounds enormous until you realize that on the scale of the galaxy, they are practically touching. They form what astronomers call a binary pair, 2 stars locked together by gravity, moving around each other in an elliptical embrace that has been ongoing for billions of years. Then, far out from that central pair, orbiting at a distance so vast it is still only loosely confirmed as gravitationally bound, sits Proxima Centauri, a red dwarf, dim, small, cool, and not a sun-like star at all. But Proxima holds a particular distinction that most people do not know. It is actually the individual star closest to us, edging out its 2 brighter companions by a small but meaningful margin. When we say Alpha Centauri is the nearest star system, Proxima Centauri is the single star in that system that has the narrowest gap to bridge. The reason Alpha Centauri captures so much of humanity's attention is not Proxima. It is the pair at the center. Alpha Centauri A is what astronomers classify as a G-type star, a yellow-white main sequence star fusing hydrogen in its core, burning with steady nuclear energy, sitting at a surface temperature of roughly 5,750 degrees Celsius, just fractionally hotter than our own Sunday. Alpha Centauri A is somewhat larger than our Sun, somewhat more luminous, and old enough, estimated at roughly 5 billion years, to have passed through a substantial portion of its stellar lifetime, to within any margin of comparison that matters for the question of planetary habitability. Alpha Centauri A is a solar twin, a star, so structurally similar to the one at the center of our own system that the differences between them are smaller than the differences between two neighboring neighborhoods in the same city. Alpha Centauri B is slightly smaller, slightly cooler, classified as a K-type star, still well within the family of stars that form planetary systems and sustain them for billions of years, still radiating enough energy at the right wavelengths to be scientifically interesting from the standpoint of what worlds might exist around it. Together, these two stars represent something our scientific imagination has long wanted to resolve. They are the nearest sun-like stellar neighborhood in existence, not the nearest stars in the sky. The sky is full of red dwarfs, closer to individual observers, depending on where they are, but the nearest stars that resemble our own sun closely enough that the question of whether they host planets similar to Earth carries the full weight of everything that question implies. If there are worlds orbiting Alpha Centauri A, those worlds formed around a star like our Sun, at a comparable distance from the galactic center, in comparable stellar conditions, with comparable elemental abundances available for planet formation. The premise of similarity is powerful, and the nearness makes the question feel answerable in a way that questions about distant stellar systems, which outnumber the nearest ones by billions to one, do not. This closeness has always carried an almost gravitational pull on the imagination. Science fiction has used Alpha Centauri as the nearest interstellar destination for as long as the genre has existed. Serious scientific projects have proposed sending spacecraft toward it. Breakthrough Starshot, a research program backed by significant private funding, proposed launching tiny laser-propelled probes toward the Alpha Centauri system at fractions of the speed of light, on a journey that would take roughly 20 years to complete, rather than the thousands of years conventional propulsion would require. The proximate reason those proposals centered on Alpha Centauri was not merely its distance. It was its distance combined with the fact that its primary stars look like ours, which made the possibility of something interesting being there feel real rather than purely speculative. But here is where the comfortable narrative about Alpha Centauri begins to develop its first fracture. Closeness and familiarity in one dimension do not automatically translate to understanding in another. We have known the distance to Alpha Centauri since the 1830s, when the Scottish astronomer Thomas Henderson made the first reliable measurement of its parallax, the tiny shift in its apparent position in the sky, caused by Earth's motion around the Sun over the course of a year. Henderson's measurement was a landmark in the history of science. For the first time, humanity knew how far away another star actually was. The answer was sobering even then. Light needed more than 4 years to make the crossing. In human terms, the nearest star was already unreachably far, but it was measurable, it was real, and knowing the distance meant that Alpha Centauri entered our scientific catalogues as something more than a bright point in the sky. It became a location, with a number attached, with a physical meaning. From that measurement onward, the knowledge about Alpha Centauri accumulated. Astronomers measured the mass of Alpha Centauri A and B, using the mechanics of their mutual orbit, the way they pull each other, the period of their revolution, the shape of the ellipse they trace out over 80 years. The orbital mechanics of a binary system are a precise tool for weighing its stars, and the Alpha Centauri pair has been weighed carefully. Alpha Centauri A has a mass of approximately 1.1 times the mass of our Sunday. Alpha Centauri B has a mass of approximately 0.9 times the Sun's mass. These numbers are known to a fraction of a percent among the most precisely determined stellar masses in our catalogues. Spectroscopic analysis has revealed the chemical composition of both stars in extraordinary detail. The abundances of dozens of elements have been measured across multiple studies, giving us a picture of the stellar material that went into forming these two suns, and that would have gone into forming any planets in the system. The metallicity of Alpha Centauri A, the relative abundance of elements heavier than hydrogen and helium, the raw ingredients for rocky planetary surfaces, is somewhat higher than the Sun's. The system is, by this measure, a good candidate for planet formation. More heavy elements in the stellar nursery means more material available for building solid worlds. The age of the system has been estimated at around 5 to 6 billion years, derived from multiple stellar evolution models that use the observed properties of the stars to work backward to when they began fusing hydrogen. This makes Alpha Centauri A and B somewhat older than our own Sun, which is itself approximately 4.6 billion years old. If planets formed around Alpha Centauri A during the early phase of the system's history, they have had between 5 and 6 billion years to evolve. On Earth, that timescale was sufficient for life to arise, diversify, develop multicellular complexity, and eventually produce organisms capable of building space telescopes. On a world around Alpha Centauri A, the same span of time has been available. All of this sounds like the profile of a well-understood system, and in the domains that the available tools could address, it is, the stars are known quantities. Their masses, temperatures, luminosities, compositions, and ages are pinned down with a precision that would have astonished Henderson when he first measured the parallax. But knowing the stars is not the same as knowing the system. A system is its stars, and everything else, the planets, the moons, the debris, the dust, the architecture of objects that formed when the protostellar cloud collapsed and settled into orbits around the newborn stars. And in that deeper sense, the dimension that matters most for the questions humans actually want answered about Alpha Centauri, the system has remained, until very recently, almost entirely dark. The planet question has hung over Alpha Centauri for as long as we have understood that stars host planetary systems. We have known since the 1990s, when the first confirmed exoplanets were detected, that planets are common around stars. We have known since the Kepler Space Telescope's observations in the 2010s that planetary systems are not merely common but nearly universal, that the majority of stars host at least one planet and many host multiple. Given this background rate of planetary occurrence, the expectation that Alpha Centauri A and B host planets is strong. The question is not whether planets should exist there in principle. The question is whether we can find them, where they are, and what they are like. And this is where the story of Alpha Centauri shifts from a story about a well-studied system to a story about an obstinate one. For all the decades of careful stellar measurement, all the precisely determined masses and temperatures and compositions, the planetary architecture of Alpha Centauri A has remained essentially invisible. Not because the planets are not there, the expectation is that they probably are, but because finding them has proven unexpectedly, almost provocatively difficult. Consider what the dominant planet hunting methods require. The radial velocity technique, which measures the tiny Doppler shift in a star's spectral lines caused by an orbiting planet's gravitational tug, is highly sensitive to signals from Alpha Centauri A and B because the stars are so bright and their spectra so rich in detail. But the binary nature of the system creates a fundamental complication. Alpha Centauri A and B are themselves moving relative to each other across the decades of their 80-year orbit. This relative motion produces its own Doppler signal in spectroscopic data, a signal that varies slowly but powerfully across the years, and that must be precisely modeled and subtracted before any planetary signal can be isolated. The required subtraction is delicate. An error in the binary orbital model propagates directly into the planet search and can produce either false positives, phantom signals that look like planets but are artifacts of the subtraction, or false negatives, where a real planetary signal gets absorbed into the binary model and disappears. This is exactly what happened in the early part of this decade. A team of astronomers announced in 2012 that they had detected a planet around Alpha Centauri b using radial velocity data, a small rocky world with an orbital period of just 3.24 days. The excitement was immediate and global. The nearest star system had a planet, but within a few years, independent analyses of the same data showed that the signal was most likely an artifact of the data analysis process, a ghost produced by the way the binary orbital model interacted with the sampling cadence of the observations. The planet was retracted, the system closed up again. This episode is worth dwelling on, not to embarrass the researchers involved. Science progresses through exactly these kinds of tests and corrections, but because it illustrates the depth of the difficulty. The radial velocity technique, which has successfully found hundreds of confirmed planets around other stars, ran into Alpha Centauri's binary architecture and produced a false result that fooled the scientific community for years. The system's complexity was not an abstract theoretical concern. It was an active, demonstrated obstacle that defeated a sophisticated detection attempt and produced genuine scientific confusion. The transit method, which looks for the faint dimming of a star's light when a planet passes in front of it, faces its own challenges at Alpha Centauri. For a transit to be detectable, the planet's orbit must be oriented so that it crosses the face of its star as seen from Earth. There is no geometric reason to assume that any planet at Alpha Centauri A is in such an orbital plane. The transit probability for a planet in the habitable zone around a Sun-like star is only a few percent, meaning roughly 9 out of 10 such planets, even if they exist, would never produce a transit detectable from Earth simply because of orbital inclination. The transit method is a powerful statistical tool when applied to vast numbers of stars, as Kepler demonstrated. It is a weak tool for a single target where the geometric alignment is uncertain and uncontrollable. Alpha Centauri has been monitored for transits, but nothing convincing has emerged. Direct imaging, actually capturing the light of a planet as a separate, resolved object near its host star, would sidestep many of these problems. A directly imaged planet does not require a special orbital inclination to be detectable. It does not require the painstaking subtraction of a binary model from spectroscopic data. It shows up as a point of light in an image, ideally moving across multiple images in a way consistent with orbital motion, carrying the signature of its own thermal emission or reflected starlight in a spectrum that can be analyzed directly. Direct imaging is the gold standard for characterizing exoplanets. It is also the hardest method to execute, for reasons that begin to crystallize the moment you apply it to the Alpha Centauri situation. The challenge with direct imaging of a planet is contrast. The star is enormously brighter than any planet. In visible light, a planet like Jupiter, around a sun-like star is about 1 billion times fainter than the star. In the mid-infrared, the thermal emission regime where planets radiate their own heat, the contrast is somewhat better, perhaps 1,000,000 to 1 for a warm gas giant. Better still, at the thermal wavelengths, where both star and planet are radiating, but the star's advantage is reduced. Even so, detecting an object 1,000,000 times fainter than a nearby source requires blocking or suppressing the bright source with extreme precision. The technique for doing this is coronagraphy, using a physical mask or optical device to block the star's direct light and reveal the much fainter environment around it. Coronagraphy works. It has been used to directly image dozens of exoplanets around distant stars, young, hot, widely separated gas giants that glow in the infrared with residual heat from their formation. But all of those successful direct imaging detections have one property in common with each other and sharply different from Alpha Centauri. The stars being observed are not overwhelmingly bright. They are distant enough and faint enough as seen from Earth that a coronagraph can suppress the stellar halo to a level where planetary signals can emerge. Alpha Centauri A is the third brightest star in the sky. Its apparent brightness, driven by pure proximity, is so extreme that the residual light leaking around any coronagraphic mask, the diffracted halo, the scattered light, the optical imperfections is itself a source of noise far larger than the planet's signal trying to emerge from underneath it. This is the first dimension of the paradox. The system that is nearest to us, and therefore most promising for detailed planetary characterization, is also the hardest system for direct imaging, precisely because of its nearness. Near equals bright. Bright equals hard to block. Hard to block means the planet, if it is there, drowns in the star's scattered light, rather than appearing clearly against a dark background. The system's proximity, the very property that makes it scientifically desirable, is the same property that makes the necessary observation technically brutal. And then there is Alpha Centauri B. The companion star sits close enough to Alpha Centauri A in the sky that it falls within the field of view of any telescope attempting to image Alpha Centauri A's environment at the angular separations relevant to habitable zone planets. Alpha Centauri B is not as bright as Alpha Centauri A, but it is far from dim. Its presence in the same field introduces a second source of scattered light, a second halo, a second structured pattern of diffracted photons that overlaps the region you are trying to study. A single star is hard enough to suppress. Two stars, one of which you cannot mask without designing a completely separate coronagraphic setup for, create a layered observational problem with no simple solution. In the language of astronomical observation, Alpha Centauri is what engineers and observers sometimes describe as a pathological target. Not pathological in any casual sense, but in the formal sense that the system's properties combine in ways that break the assumptions underlying most standard observational approaches. Too bright for easy coronagraphy, too binary for clean radial velocity searches, too geometrically uncertain for transit reliance, and moving too quickly across the sky because of its closeness. It has a measurable proper motion that other distant targets lack to be trivially reobserved across multiple sessions without careful planning. For all these reasons, the planetary architecture of the nearest sun-like stellar system in the sky has sat in a state of productive ignorance for decades. Productive because the attempts to break through the observational barriers generated real scientific knowledge about the system's constraints, about what was likely or unlikely based on stability analyses, about the dynamical environment that any planet would have to survive in, and ignorance because, despite all the effort and all the technique, we had not actually seen a planet there. We had not even come close enough to seeing one that we could make confident claims about where one was or was not. Then came the James Webb Space Telescope. And before we can understand what Webb saw and what the disappearance of what it saw means, we need to sit with one more aspect of Alpha Centauri's character that has received less attention than it deserves in most discussions of this story. We need to understand what the binary geometry of the system has done over billions of years to the space where planets might live. The gravitational relationship between Alpha Centauri A and Alpha Centauri B is not a distant, abstract thing. These two stars are close enough in astronomical terms that their mutual gravity has been shaping the structure of any planetary disk around Alpha Centauri A since the system was young. When a star forms and its surrounding disk of gas and dust begins to settle and cool and develop structure, it does so under the influence of every gravitational source in the environment. For Alpha Centauri A, one of those gravitational sources is its stellar companion. Alpha Centauri B is not so far away that its influence can be ignored. It tugs on the disk material around Alpha Centauri A, driving spiral waves through it, truncating it at certain radii, perturbing planetesimals, the building block objects that eventually coalesce into planets in ways that differ from what would happen in a single star system. Theoretical models of planet formation in binary stellar systems show a range of outcomes depending on the binary separation, the mass ratio of the two stars, and the geometry of the disk. For Alpha Centauri A and B, with their current binary parameters, the models generally suggest that planet formation is possible in the inner regions of Alpha Centauri A's disk within a few astronomical units of the star, but becomes increasingly difficult at larger separations where the companion's perturbations grow more disruptive. The outer disk, where the giant planets of our own solar system formed, is effectively off-limits for stable planet formation around Alpha Centauri A, because Alpha Centauri B's gravity would have stirred that material too violently for it to accumulate into planets. This means that if Alpha Centauri A has planets, they are most likely in the inner system, the same orbital territory that is also closest to the star's blinding light, and therefore hardest to image, the habitable zone of Alpha Centauri A, where a rocky world might maintain surface liquid water, sits at roughly 1 to 1.7 astronomical units from the star. This is the target range, and it is also the most technically demanding range for coronagraphic direct imaging, because the closer a planet is to its star, the smaller the angular separation between them as seen from Earth, and the deeper inside the coronagraphic mask and its surrounding halo the planet's signal lies. Everything about the Alpha Centauri system, in other words, is arranged to make the scientific questions we most want to answer about it the hardest questions to answer. The stars that most resemble our Sun are too bright to look past easily. The binary geometry that makes the system interesting from a formation standpoint is the same geometry that complicated the radial velocity searches and added a second blinding light source to the imaging problem. The planet-forming zone that is relevant to habitability is the zone closest to all of this difficulty. The system has not been obstinate by design. The universe has no design in that sense, but it has, through the coincidence of its physical properties, managed to align its most interesting characteristics with the most challenging observational constraints. For generations, those constraints were insurmountable. Webb was the first instrument capable enough, flexible enough, and operating at the right wavelengths to make a serious attempt. When the results of that attempt came in, when the August 2024 observations were processed and analyzed, and a faint point source emerged from the carefully subtracted data, the reaction from the scientific team was exactly what you would expect from people who had been looking at this system through inadequate windows for their entire careers. The object popped out so clearly that it could not be ignored. And then the follow-up observations came back empty, and the story of the nearest sun-like stellar system in the sky became, in the space of 8 months, both clearer and stranger than it had been for the preceding 2 centuries. That is where we go next, into the specifics of what Webb did, how it did it, and why the result it produced tells us something that goes deeper than a single planet candidate. To understand what Webb actually did when it looked at Alpha Centauri A, you have to understand something about the nature of the problem it was solving, and why that problem is different from almost everything else the telescope does. Webb is famous for looking far. Its primary scientific mission is cosmological and astrophysical in the grandest senses of those words. Probing the first light of the universe, studying the formation of galaxies in the early cosmos, characterizing the atmospheres of exoplanets around distant stars through spectroscopic analysis of starlight filtered through those atmospheres. In all of these cases, the objects Webb is studying are faint. Some of them are almost incomprehensibly faint. The early galaxies Webb was designed to detect are separated from us by billions of light years, their light stretched and dimmed by the expansion of space itself, arriving at Webb's mirror as whispers of infrared radiation that require careful accumulation across minutes or hours of observation. Webb's extraordinary sensitivity, its large mirror, its precise pointing, its infrared-optimized detectors operating at temperatures a few degrees above absolute zero, was built for this regime. For the challenge of finding and characterizing signals that are nearly invisible against the cosmic background, the Alpha Centauri A observation is a different kind of hard. It is hard not because the signal is too faint in any absolute sense, but because it is too close to something overwhelmingly bright. The planet candidate, if it exists, is radiating thermal infrared light at a level that, by the standards of faint cosmic sources, is actually not negligible. A Saturn mass gas giant at around 2 astronomical units from a star like Alpha Centauri A, at the age of several billion years, should emit measurable thermal radiation in the mid-infrared wavelengths that Webb's MIRI instrument is sensitive to. The planet is detectable in principle. The problem is that it sits next to a star that, as seen from Earth, is among the brightest objects in the sky, and that stellar brightness overwhelms the planet's signal, the way a searchlight overwhelms a candle flame at close range. Webb's mid-infrared instrument MIRI is the telescope's thermal infrared workhorse. It operates at wavelengths between 5 and 28 micrometers, a regime where cool objects like gas giant planets emit their stored heat, and where the contrast between a star and a planet, while still severe, is less extreme than at shorter wavelengths. The specific observation mode used for Alpha Centauri A was MIRI's coronagraphic imaging mode at 15.5 micrometers, a filter called F1550C. This wavelength was chosen deliberately. At 15.5 micrometers, a gas giant planet at the relevant distance from Alpha Centauri A should be bright enough in thermal emission to rise above the background noise of the observation. while the star-to-planet contrast ratio is somewhat more manageable than it would be in visible or near-infrared light. The coronagraph in MIRI F1550C mode uses what is called a 4-quadrant phase mask, a device that exploits the wave nature of light to create destructive interference at the position of the bright star, effectively cancelling out the star's direct light through phase manipulation rather than physical blocking. Phase masks can, in principle, achieve better stellar suppression than simple opaque disk coronagraphs because they exploit light's wave properties rather than just stopping photons with a physical barrier. But they work best for stars positioned with extreme precision behind the mask, and their performance degrades when conditions are not ideal, when the star's position drifts slightly relative to the mask, when the telescope's optical quality varies, or when a second bright source contaminates the field. The team that observed Alpha Centauri A with Webb developed what they described as a custom observing sequence that was not part of Webb's standard operational repertoire before this observation. Standard coronagraphic observations with MIRI assume a single bright target star, a relatively stable pointing situation, and a selection of reference stars that closely match the target in brightness and spectral energy distribution, so that the reference star's diffracted halo can be used as a template for subtracting the target star's halo. The Alpha Centauri observation broke several of these assumptions simultaneously. First, there are 2 bright stars in the field, not one. Alpha Centauri B does not fall behind the coronagraphic mask. It sits offset from the mask center, pouring its own light into the observation, scattering across the detector in a pattern that overlaps the region where any planet around Alpha Centauri A would appear. The coronagraph suppresses Alpha Centauri A's direct light. It does nothing about Alpha Centauri B. The team had to handle Alpha Centauri B through a combination of physical positioning, placing the 2 stars in orientations relative to the mask and detector that minimized contamination, and computational subtraction, modeling the expected point spread function of Alpha Centauri B at its specific position in the field, and removing that contribution from the data after the fact. The point spread function of a star in a telescope image is the full pattern of light that the star produces on the detector, including all the diffracted rings, spikes, and halos that result from the star's light interacting with the telescope's optics, support structures, and detector imperfections. For a telescope with a simple circular mirror, the point spread function has a relatively simple analytical form. The familiar airy disk pattern of concentric rings, decreasing in brightness outward from the center. For Webb, the situation is more complex. Webb's primary mirror is composed of 18 hexagonal segments, each independently positioned and angled to bring all their reflected light to a common focus. This segmented architecture, while enabling the mirror to be folded for launch and then unfurled in space, creates a more complex diffraction pattern than a monolithic circular mirror would produce. The gaps between segments, the hexagonal geometry of the individual mirrors, the support structure connecting them all, each of these contributes characteristic features to the point spread function that a reference star subtraction approach must account for. For nearby, bright stars moving quickly across the sky like Alpha Centauri, finding a suitable reference star is itself a challenge. The reference star must be bright enough to generate a usable signal in a short exposure without saturating the detector, but not so bright that it approaches Alpha Centauri A's extreme luminosity and creates its own saturation problems. It must have a similar color, a similar spectral energy distribution, so that the thermal emission pattern from star to star is consistent enough that one's halo can serve as a model for the others. And it must be observable from Webb's orbital position within a reasonable time window before or after the target observation, so that the telescope's thermal state and pointing characteristics are comparable between the target and reference observations. The operations team at the Space Telescope Science Institute, working with the science team, spent considerable time developing the strategy for these observations. The precise language used in the published papers captures the effort involved. These observations required a custom observing sequence just for this target, one that their extra effort paid off spectacularly to achieve. The phrase "extra effort" in this context is a significant understatement. Custom observing sequences for space telescopes involve validation at multiple levels, simulation, testing against calibration data, review by engineering teams familiar with the telescope's behavior in various configurations, and scheduling in a way that allows the observation to actually be executed when the target is accessible and the competing demands on telescope time permit. Webb's scheduling constraints are more complex than those of a ground-based telescope, which can in principle be repointed at any target visible above the horizon on any given night. Webb orbits at the gravitationally stable Lu-2 point, roughly 1.5 million kilometers from Earth in the anti-Sun direction, maintaining a fixed orientation relative to the Sun-Earth line to keep its sun shield, protecting the cold optical assembly. This means Webb can only observe targets in a specific range of angular distances from the Sun at any given time, and its scheduling is a complex optimization across hundreds of approved programs, each competing for time across multiple instrument modes and observing configurations. Getting time on a target as bright and as geometrically challenging as Alpha Centauri A required justifying not just the scientific case, but the operational feasibility across all these constraints. When the August 2024 observations were finally executed, the sequence proceeded through multiple exposures at different telescope roll angles, rotational orientations of the spacecraft around the optical axis that allowed the diffraction pattern from Alpha Centauri A to be observed in multiple configurations. By combining observations taken at different roll angles, the team could better distinguish between the fixed pattern of diffraction artifacts, which rotates with the telescope, and any real astrophysical source in the field, which maintains a fixed position on the sky, regardless of how the telescope is oriented. A real planet would appear at the same sky position in all roll angles. A diffraction artifact or ghost image would shift its position as the telescope rotates. This roll angle diversity technique is one of the most powerful tools in the coronagraphic imager's arsenal for distinguishing planets from instrumental artifacts, and the team applied it systematically to the Alpha Centauri A data. After blocking Alpha Centauri A's direct light with the 4-quadrant phase mask, subtracting the contribution of Alpha Centauri B computationally, applying reference star subtraction to model and remove the structured halo of diffracted light from Alpha Centauri A, and combining the multiple roll angle exposures, a signal emerged. The papers designated it S1 for source 1. It appeared as a compact point source, the paper's way of saying it was not extended or diffuse, but concentrated in the way a planet or a star would be, rather than spread out in the way a galaxy or a dust cloud would be, at a position roughly 2 astronomical units from Alpha Centauri A in projected sky separation. The signal was over 10,000 times fainter than Alpha Centauri A itself. Without the coronagraph, Without the subtraction, without all the layers of processing, it would have been completely invisible, buried in the star's halo like a word erased under layers of paint. Through all the technique that the team had developed, it came through clearly enough that even a first look at the processed data revealed it immediately. The immediate response of the science team was skepticism of exactly the right kind. Not the dismissive skepticism that says this cannot be real without examining the evidence, but the productive skepticism that says we must explain this in every mundane way before we are allowed to consider the exciting interpretation. They worked through every alternative to a real planet that they could construct. Background galaxies were the first and most important alternative to test. The sky behind the Alpha Centauri system contains other objects, distant galaxies, faint stars in the background, quasars and other extragalactic sources distributed across the field. A background galaxy at the right position in the sky would appear as a point source in MIRI's images if it were sufficiently compact, and it would not move relative to the background sky from one observation epoch to the next. The team examined the known properties of background sources expected in that region of sky, checked the brightness and morphology of S1 against what galaxy populations predict, and found that a background galaxy was not a satisfying explanation for the object's properties. Passing asteroids were considered next. Asteroids in our own solar system move across the sky at rates that are fast compared to the integration times of a deep coronagraphic observation. An asteroid crossing the field during an exposure would smear across the detector, producing a streak rather than a point source, and would not repeat at the same position in subsequent observations taken minutes or hours later. The morphology of S1 was point-like, not extended in a streak, and its position was consistent across the multiple exposures within the August observation sequence. It was not an asteroid. Known optical artifacts, specific to the MIRI coronagraph's 4-quadrant phase mask, include certain characteristic ghost images that appear at predictable positions relative to the star when the coronagraphic alignment is slightly imperfect, and diffraction residuals from the hexagonal mirror segments that produce bright spots at specific angular positions relative to the mask center. The team worked through the expected positions and brightnesses of these artifacts and showed that S1 did not match any of them in position, brightness, or behavior across roll angles. If S1 were a diffraction artifact or optical ghost, it would appear at a predictable position that rotates with the telescope as roll angle changes. S1's position did not rotate with roll. It behaved like a fixed sky source, not an instrumental effect. After all of this analysis, what the team was left with was a signal they could not explain through any mundane mechanism they had been able to test. This is not the same as saying the signal must be a planet. The inability to identify an alternative explanation does not logically force the positive conclusion. There might be mundane explanations that were not thought of, or were not testable with the available data, or that would only become apparent with additional observations at different wavelengths or different times. Science is careful about exactly this kind of reasoning, and the team was careful. They described S1 as a candidate, as a robust signal, as strong evidence, not as a confirmed planet. The distinction matters, and it is honest. The follow-up observations were necessary for the same reason that first detections are always insufficient in direct imaging. A planet should move. Over weeks or months, a gas giant at 2 astronomical units from a star completes a meaningful fraction of its orbit. The angular position of a planet relative to its star should shift measurably from one observation to the next, tracing an arc that is consistent with Keplerian orbital mechanics. If S1 is a planet, subsequent observations should find it at a slightly different position around Alpha Centauri A, offset in the direction and by the amount that the orbital motion predicts. This is the definitive test. This is how a candidate becomes a confirmed detection. The team applied for and received Director's Discretionary Time, a category of Webb allocation reserved for time-sensitive, high-priority scientific opportunities that arise unexpectedly and need telescope access outside the normal scheduling cycle. Director's Discretionary Time is precious and competed for intensely. Its allocation to the Alpha Centauri follow-up reflects the scientific community's recognition that the August 2024 signal was important enough to justify expedited access to the telescope. 2 additional observation sets were scheduled, one in February 2025 and one in April 2025, both targeting Alpha Centauri A with the same MIRI coronagraphic setup used in August. The February 2025 observations encountered technical difficulties. The papers describe the February session as compromised. Only a single successful roll angle was obtained, rather than the multiple rolls that the roll angle diversity technique requires for robust artifact discrimination. Additionally, there was a pointing offset, a small but meaningful mismatch between Alpha Centauri A's actual position and the reference observation's assumed position behind the coronagraphic mask that degraded the quality of the reference star subtraction. A pointing mismatch of around 10 milliarcseconds sounds tiny, but for a coronagraph that works by precisely aligning the star's light with a phase mask designed to cancel that light through interference, even small pointing errors reduce the depth of suppression, allowing more stellar light to leak into the image and raising the noise floor above which a planet's signal must emerge. These are not excuses for a negative result. They are the honest scientific description of what happened, and they carry real epistemic weight. A non-detection in clean, well-executed data would be a stronger negative result than a non-detection in compromised data. The February 2025 non-detection tells us something, but less than a clean non-detection would tell us. The April 2025 observations were better executed, but S1 was still absent from both. The planet candidate that had emerged so clearly from the August 2024 data was, in the February and April follow-ups, nowhere to be found. The team faced this disappearance directly. They described it plainly. We are faced with the case of a disappearing planet, and rather than treating the disappearance as definitive evidence that the August signal was a false positive, which it might be, and which they acknowledged, they turned to what orbital physics could tell them about whether the disappearance is consistent with the planet hypothesis. This is the right scientific move. The question is not just what was seen and what was not seen, but whether those two outcomes together constrain the parameter space of possible explanations. To investigate this, the team used computer modeling to simulate millions of potential orbits for a planet with the properties suggested by the August 2024 detection, an object with a brightness consistent with a Saturn mass gas giant, sitting at a projected separation of roughly 2 astronomical units from Alpha Centauri A in August 2024. They varied the orbital parameters across the full range of possibilities consistent with the detection geometry. Different orbital periods, different eccentricities, different inclinations, different orientations of the orbit in space. For each simulated orbit, They asked a specific question. Would this orbit place the planet at a separation from Alpha Centauri, large enough to be detected by Webb's coronagraph in February and April 2025? The results were striking in their implications. For a substantial fraction of the orbital parameter space, roughly half of all simulated orbits consistent with the August detection, the answer was no. These orbits would carry the planet inward toward Alpha Centauri A between August 2024 and the spring of 2025, reducing its projected separation from the star to the point where it would fall within the coronagraphic mask's blocked region, or within the innermost part of the stellar halo where the background noise from scattered starlight is high enough to bury the planet's signal. In these scenarios, the planet is not absent. It is hidden, swept behind the star's light by the geometry of its own orbital motion, invisible to Webb during exactly the windows when the follow-up was attempted. The team also incorporated other data into their analysis. The Very Large Telescope's VISA mid-infrared camera, as part of the NEAR project's observations of Alpha Centauri in 2019, had detected a tentative signal at a position in the Alpha Centauri A system that was consistent with a companion object. That 2019 signal had not been confirmed at the time and had not been the subject of a major published claim, but it sat in the archival record as a data point that the team could now fold into their orbital modeling. A planet that was at a certain position in 2019 and at another position in August 2024 must have moved in a way consistent with orbital mechanics. The combination of these two potential detections, separated by approximately 5 years, constrained the orbital period and therefore the orbital size of the candidate in ways that the August 2024 data alone could not. The orbital models that emerged from this analysis suggest a planet with an eccentric orbit. The papers describe an eccentricity of approximately 0.4, meaning the orbit is significantly stretched rather than circular, with the closest approach to Alpha Centauri, A being substantially less than the average orbital distance, and the farthest point substantially greater. This eccentricity is not surprising in the context of the binary system's gravitational environment. Alpha Centauri B's influence can pump eccentricity into planetary orbits around Alpha Centauri A over geological timescales through a mechanism called Kozai-Lidov oscillations, which can cause a planet's orbital eccentricity and inclination to vary in a coupled way over long periods. A planet that started in a more circular orbit might have been pushed into a more eccentric one by these perturbations over the billions of years the system has existed. The suggested orbit is also apparently inclined with respect to the orbital plane of the binary pair itself, another signature consistent with binary system gravitational processing of an inner planet's orbital parameters. An eccentric, inclined orbit has specific observational consequences that are important for planning future work. A planet in a highly eccentric orbit spends different amounts of time at different orbital separations from its star. Near the close approach, it moves quickly, spending relatively little time at small separations. Near the far point, it moves slowly, spending relatively more time at large separations. This means that, for direct imaging, which needs the planet to be at a large enough angular separation from the star to be outside the coronagraph's inner working angle, the windows of opportunity are not evenly distributed across the orbital period. They cluster around the orbital phases where the planet is near its farthest point from the star. Knowing the orbit well enough to predict when those windows will occur is crucial for scheduling follow-up observations effectively. The team does not yet know the orbit well enough to make those predictions with high confidence. The available data points the 2019 tentative detection, the August 2024 robust detection, and the February and April 2025 non-detections constrain the orbital parameter space, but do not pin it down to a unique solution. Many different orbital configurations remain consistent with the observations. Some of them would predict that the planet is detectable by Webb again within the next year or two. Others would predict a longer wait. And some fraction of the orbital configurations still correspond to scenarios where S1 is not a planet at all, where the August 2024 signal was something else, a transient event or an unidentified artifact, and the candidate planet hypothesis is simply wrong. This is the situation the nearest Sun-like stellar system has placed us in as of the time this story is told. We have the most powerful space observatory ever built. We have decades of preparation and theoretical analysis. We have a custom observation sequence developed specifically for this target. We have a robust detection in August 2024, carefully scrutinized against every mundane alternative the team could test. And we have two subsequent non-detections, one of them technically compromised, that are consistent with, but do not prove the hypothesis that the candidate is a real planet in an eccentric orbit that swept it behind its star's glare during the follow-up windows. We have a disappearing signal and a system that is, under the gaze of the best instrument humanity has aimed at it, still resisting the kind of clean, unambiguous answer that the word understanding implies. The magnitude of the effort required to get even this partial picture deserves emphasis. The coronagraphic mode used for this observation is, in the words of Pierre-Olivier Lagarde of CEA France, and one of the French leads for MIRI's development, among the most demanding observations we have done so far with MIRI's coronagraph. These are the words of someone who helped build the instrument, who has watched it perform across its full range of operational modes since commissioning, and who characterizes the Alpha Centauri A observations at the high difficulty end of what the instrument is capable of doing. Not the routine operation of a powerful tool, but the edge of what the tool can achieve under the most challenging conditions it has been asked to meet. This is the texture of what it means to try to understand the nearest Sun-like stellar system. Instrument teams spending years preparing, operations teams developing new procedures, science teams working through every alternative explanation. Webb's full capability deployed at the limit of its performance envelope. And the result, a tantalizing signal, a disappearance, a parameter space of possible orbits, and a system that has given us a first glimpse of something significant, while simultaneously making that glimpse ambiguous enough to require substantial additional work before any certainty can be claimed. The nearest major stellar system in the sky looked through Webb's coronagraph, not like a solved problem but like a question that has been sharpened without yet being answered, and understanding why demands we look more closely at what Webb actually did and what it was up against, which is exactly where the third part of this story must go. There is a specific kind of scientific frustration that has no clean name, but that every researcher who has worked on an elusive problem knows deeply. It is not the frustration of failure. Failure at least closes a question. It is the frustration of a partial answer that opens more questions than it resolves, that leaves you with more certainty about your uncertainty than you had before, that proves something happened without proving what that something was. The Alpha Centauri, a planet candidate, as the situation stood after the April 2025 follow-up observations, sat exactly in this space. A robust detection in August 2024. 2 non-detections in early 2025. An orbital model that explained both outcomes, but did not prove either. A system that had offered up something real seeming and then taken it back on exactly the schedule that would be most maddening to anyone trying to characterize it. To fully appreciate why this situation is so consequential, we need to inhabit the detection event itself with more precision than the broad strokes of the story so far have allowed. When the August 2024 data came off the telescope and into the hands of the analysis team, they were not looking at an image in any simple sense. They were looking at the output of a layered processing pipeline that had removed the direct stellar light, modeled and subtracted the contribution of Alpha Centauri b, applied reference star subtraction to depress the structured halo of diffracted light around Alpha Centauri a, and combined multiple roll-angle exposures to distinguish fixed sky sources from rotating instrumental artifacts. What survived all of that processing, what remained visible after every layer of subtraction and correction and combination, was S1. The signal was point-like, compact, located at a position in the image corresponding to a sky separation of approximately 2 astronomical units from Alpha Centauri A in projected distance, projected because we are seeing the orbit from some angle, not necessarily face-on. So, the true 3-dimensional separation might be somewhat different from the apparent sky separation. The signal's brightness in the MIRI F1550C band at 15.5 micrometers of wavelength was consistent with what a Saturn mass gas giant should emit in thermal infrared radiation at that approximate distance from Alpha Centauri A and at the system's age of approximately 5 billion years. A Saturn mass planet has spent 5 billion years slowly cooling from the heat it accumulated during formation, radiating that stored energy as thermal infrared glow. The amount of infrared emission expected from such a world, at such an age, at such a distance from us, matches what S1 showed in the data. This consistency between the observed brightness and the theoretical prediction for a Saturn mass gas giant is not a coincidence that proves the interpretation. It is a constraint that survives the alternative explanations. A background galaxy at the right brightness would need to have a very specific apparent size and morphological profile. It would need to be compact enough to appear point-like in MIRI's images, which eliminates most extended source galaxies. A transient astrophysical event, such as a flare from some exotic source, would not be expected to appear only in the thermal infrared at exactly the right brightness level for a planet, while showing no counterpart at other wavelengths. An optical artifact would have the wrong positional behavior across roll angles. None of the alternatives survived all the tests simultaneously. The planet hypothesis survived all of them. The team also compared the August 2024 detection with archival data from the Very Large Telescope's VISA instrument, obtained in 2019 as part of the NEAR project. That earlier observation had found a tentative candidate at a similar location in the Alpha Centauri A system. The NEAR data had not produced a high-confidence detection on its own. The ground-based observations were limited by atmospheric turbulence, by the VISA instrument's less capable coronagraphic suppression compared to Webb, and by the shorter integration time available. But the tentative signal existed in the archival record, and the question of whether the August 2024 Webb detection and the 2019 NEAR tentative signal might be the same object moving along a consistent orbit was a scientifically important one. If they are the same object, then the 5-year baseline between 2019 and 2024 provides powerful constraints on the orbital period and therefore the orbital size. A planet's position changes by an amount that depends on how much of its orbit it has completed in the intervening time. A planet with a short orbital period, say 1 to 2 years, would have completed multiple full orbits in 5 years and would have returned to a similar part of its orbit in 2024 compared to 2019. A planet with a longer period, 3 to 5 years, would have completed only part of an orbit and would have appeared in a different quadrant of the system. The apparent positions of the tentative 2019 signal and the robust 2024 detection, and the geometry of how those positions relate to Alpha Centauri A, constrain which orbital periods are physically consistent with both observations. The team ran their simulation of millions of orbital configurations, incorporating both the 2019 and 2024 data points, along with the 2025 non-detections. The resulting family of consistent orbits suggests an orbital period of a few years with the most favored range, placing the orbital period somewhere between roughly 2 and 5 years. An orbit in this period range corresponds to a semi-major axis of roughly 1.5 to 2.5 astronomical units, depending on the exact eccentricity. This is entirely consistent with what the planet formation stability analysis for the Alpha Centauri A and B binary system predicts for the inner stable zone, the region where planets can survive the binary's gravitational influence over geological timescales without being perturbed into unstable, star-crossing, or ejected orbits. The apparent eccentricity suggested by the modeling around 0.4 is particularly interesting because it has a specific physical interpretation in the context of the binary system. A circular orbit at around 2 astronomical units around Alpha Centauri A would be stable, according to the dynamical models of the system, but it need not remain circular. The mechanism by which binary systems perturb planetary orbits is well understood theoretically. Alpha Centauri B, orbiting at an average of 23 astronomical units from Alpha Centauri A, on an ellipse that brings it as close as 11 astronomical units at periastron, exerts a time-varying gravitational torque on any planet in Alpha Centauri A's inner system. This torque can drive oscillations in the planet's orbital eccentricity and inclination through a process that operates on timescales of hundreds of thousands to millions of years. Over the system's multi-billion-year lifetime, these oscillations could have evolved the planet's orbit from something initially more circular to something more elongated, while also tilting the orbital plane relative to the binary's own orbital plane. An eccentricity of 0.4 means the planet's distance from Alpha Centauri varies by a factor of roughly 3 between closest and farthest approach. At its closest, called periastron, the planet would sit approximately 1.2 astronomical units from the star. Inside the range, typically considered the inner edge of the habitable zone for a star of Alpha Centauri A's luminosity. At its farthest apastron, it would sit at approximately 2.8 astronomical units, well outside the habitable zone, in the cooler outer reaches of the inner system. Over the course of one orbit, the planet would experience a swing in stellar irradiation by a factor of roughly 5 or 6, receiving far more energy per unit area when close and far less when distant. For the planet itself, this eccentricity cycle would drive significant variations in atmospheric dynamics. A gas giant in an eccentric orbit does not simply sit at a fixed temperature. It warms as it approaches its star and cools as it recedes, with the time scale of that warming and cooling determined by the atmospheric heat capacity and the orbital period. For a planet with Saturn's approximate mass, the atmospheric response time is probably long compared to the orbital period, meaning the planet's upper atmosphere might lag significantly behind the varying stellar input, maintaining a kind of thermal inertia that buffers the temperature swings. But the deep atmospheric dynamics, the cloud structures, the chemistry of the upper troposphere, all of these would be modulated by the orbital eccentricity in ways that differ profoundly from the relatively steady-state conditions a circular orbit planet would experience. The implications of the eccentricity extend beyond the planet itself to anything the planet might have influenced in the inner system. In our own solar system, Jupiter's gravitational influence shaped the asteroid belt, diverted comets from the outer solar system into the inner regions, and affected the delivery of water and organic material to the early Earth. A gas giant in the habitable zone of Alpha Centauri A, with an eccentric orbit that repeatedly takes it from inside to outside that zone, would have had complex and varied gravitational effects on any smaller bodies in the system. It would have scattered material across a wide range of orbital energies, potentially delivering volatile-rich bodies to the inner system during some phases of its orbit and clearing other regions during other phases. The presence of a gas giant at this location, if confirmed, would fundamentally alter the theoretical picture of what the rest of Alpha Centauri A's planetary system looks like, how many other worlds it contains, where they are, and what their dynamical histories have been. This is one of the most important aspects of the discovery that tends to get lost in the simplification of the story to planet found, planet lost. The planet candidate's significance is not limited to whether it is or is not there. If it is there, it carries within its orbital parameters a record of the gravitational history of the system, the influence of the binary companion, the accumulated perturbations of billions of years, the dynamical processing that distinguishes this system from a single star system in ways that are both theoretically interesting and observationally constraining. The orbit speaks. Even an unconfirmed candidate, carefully modeled against all available data, begins to tell us things about the system's architecture that we could not have known before Webb looked. And if S1 is not a planet, if future observations or theoretical analysis eventually identifies it as something else, the observation still will not have been without value. The techniques developed for this observation have advanced the field of coronagraphic imaging in several ways. The custom observing sequence, the methods for handling the contribution of a binary companion when in the coronagraphic field, the approaches to reference star subtraction for extremely bright, fast-moving nearby targets. All of these will inform future coronagraphic programs targeting other nearby bright stars. Webb's coronagraphic capability is still being developed and refined. Each challenging observation teaches the teams operating the instrument something new about its behavior at the edges of its performance envelope, and that knowledge flows into better observations of every subsequent target. The February 2025 technical difficulties are a case in point. The pointing mismatch that degraded the coronagraphic suppression quality in that observation was not anticipated before it happened. It emerged as a real consequence of attempting an observation at the extreme limits of the Panda instrument's operational design. Understanding why the mismatch occurred and developing procedures to prevent it in future observations of similarly challenging targets is valuable engineering knowledge that did not exist before this observation was attempted. The Alpha Centauri A program Whatever its ultimate scientific outcome, is serving as a development testbed for coronagraphic techniques that the field will need for future searches, not just for more planets around Alpha Centauri, but for planets around other nearby bright stars that pose similar observational challenges. There are several such stars within 10 to 15 light-years of the Sun. Tau Ceti, at 12 light-years, is a G-type star slightly less massive than the Sun, with multiple planet candidates from radial velocity data. Epsilon Eridani, at 10.5 light-years, is a K-type star with a confirmed debris disk and circumstantial evidence for at least one large planet. Epsilon Indi, at 11.8 light-years, is a K-type star with a directly imaged super-Jupiter companion at wide separation discovered within the last few years. These systems, like Alpha Centauri, are close enough that direct imaging of inner planets is, in principle, within reach of current or near-future instrumentation, but challenging for the same reasons of brightness and proximity. What is learned from the Alpha Centauri? A coronagraphic campaign with Webb directly informs the design and execution of future campaigns targeting these other nearby systems. The broader program of searching for planets around the nearest Sun-like stars is, at its core, driven by a single scientific imperative. Proximity matters for characterization in a way that nothing else can compensate for. Finding a planet around a star 12 light-years away is scientifically valuable. Finding the same planet around a star 4 light-years away is transformatively more valuable because the angular size of any structures around the nearest star is roughly 3 times larger as seen from Earth. The apparent brightness of any companion is roughly 9 times greater, and the potential for follow-up spectroscopic characterization is proportionally more powerful. At 4 light-years, a gas giant's atmosphere might be analyzable in ways that are simply not possible at 12 or 20 or 100 light-years. The instruments required are ambitious, but they are not fantastical. They are variations on technology that exists and is being developed. The extremely large telescope currently under construction in the Atacama Desert of Chile represents the most immediate next step in this characterization program. With a primary mirror 39 meters in diameter, substantially larger than Webb's 6.5-meter mirror, and extreme adaptive optics systems capable of correcting for atmospheric turbulence in real time, the ELT will achieve angular resolutions and contrast ratios at certain wavelengths that Webb cannot match. Ground-based adaptive optics systems, when they work at their best on stable nights at high-altitude dry sites, can partially compensate for the blurring effect of Earth's atmosphere to a degree sufficient for high-contrast imaging of nearby stellar environments. The ELT's aperture means it collects roughly 36 times as much light as Webb, an enormous advantage for detecting faint companions next to bright stars. Because more light means better characterization of the stellar halo, and therefore better subtraction of that halo to reveal what lies beneath it. For Alpha Centauri A specifically, the ELT will be able to observe the system from the southern hemisphere. The Atacama site is ideally positioned for southern sky targets and will be able to respond quickly when orbital models predict that the planet candidate is at a favorable separation. A ground-based telescope with adaptive optics can, in principle, be triggered to observe Alpha Centauri A on short notice during good weather conditions, without the long scheduling lead times required for a space observatory with a full queue of pre-allocated programs. This flexibility is valuable when the observation target is a planet in an eccentric orbit that may present favorable viewing windows of limited duration. Whether the ELT or future Webb observations will confirm or refute the S1 candidate remains to be seen. The science team is continuing to analyze the available data, to refine the orbital models, and to develop observing strategies for future epochs that maximize the probability of catching the candidate at a detectable orbital phase. Additional directors' discretionary time observations have been discussed. The community is aware that this is a high-priority target and that the combination of Webb and the ELT, working in complementary wavelength regimes and with complementary observational strategies, represents the strongest possible case for eventually resolving the ambiguity. But the ambiguity itself is worth sitting with before we move past it, because it is not a temporary inconvenience on the way to a clean answer. It is a feature of the scientific situation that reveals something fundamental about the Alpha Centauri system and about our relationship to it. The ambiguity exists because the system is geometrically and photometrically complex in ways that even the most powerful observatory ever built cannot fully resolve in a small number of observation epochs. The system has an architecture, a binary geometry, a candidate planet with an eccentric orbit, a brightness that overwhelms coronagraphic suppression near the inner working angle that combines to create a detection environment where signal and non-signal are not cleanly distinguishable from each other with the data currently in hand. This is the system that has been in our sky for as long as we have been looking up. This is the system that has accumulated 2 centuries of precise stellar measurement without revealing what it actually contains. This is the system that required the most demanding coronagraphic observations ever attempted with Webb to produce a single detection epoch, followed by 2 ambiguous non-detections that are consistent with the planet hypothesis, but do not confirm it. The nearest Sun-like stellar system in the sky is not behaving like a solved problem that Webb has finally cracked open. It is behaving like a system that is considerably harder to understand than its familiarity had promised, and the deeper you go into what that means, the more it challenges the assumptions we did not even know we were making. That is the thread that the final part of this story must pull until it unravels something true. Every scientific discovery has 2 dimensions that are easy to conflate but important to keep separate. The first dimension is what was found, the specific measurement, the specific signal, the specific data point that the observation produced. The second dimension is what that finding means, the broader context it shifts, the assumptions it revises, the picture of the universe it alters. The Alpha Centauri, a planet candidate, is a relatively modest finding in its first dimension. A signal in one epoch of Webb data, unconfirmed, consistent with a Saturn mass gas giant, associated with a disappearance in follow-up observations that orbital modeling can partially explain. In the hierarchy of exoplanet discoveries, it is a candidate, not a confirmed detection, and confirmed detections currently number in the thousands. The first dimension is significant, but bounded. The second dimension is where the genuine disturbance lives. And understanding it requires stepping back from the specific technical narrative of coronagraphy and orbital modeling and looking at what the observation implies about the category of thing Alpha Centauri A belongs to, and what that, in turn, implies about how we have been thinking about our nearest stellar neighbors. We organize our understanding of the universe around scales of proximity. The nearest things are the best known, the things we have studied longest, from closest range, with the most instruments, are the things we understand in the most dimensions. This is not just an assumption, it is a reasonable empirical generalization that has been true across most of the history of science. The geology of our own planet is better understood than the geology of Mars. The physics of our own sun is better understood than the physics of distant stellar types we can only observe from afar. The planetary system of our own sun is better understood than any other planetary system in the universe. Proximity equals data. Data equals understanding. But the Alpha Centauri, a planet candidate, reveals a specific way in which this scaling breaks down a way that has not been fully articulated in the public discussion of this result, and that carries significant implications for how we think about the nearby universe. The breakdown occurs specifically in the domain of planetary characterization around nearby bright stars. And it occurs not because proximity provides less data in absolute terms. Alpha Centauri A gives us more photons per second than any other G-type star, but because the kind of data that proximity provides is the wrong kind for the specific question being asked. Consider the nature of the information that the extreme brightness of Alpha Centauri A encodes. Every photon that arrives at Webb from Alpha Centauri A carries information about the star, its temperature, its composition, its velocity, its magnetic activity, the structure of its photosphere and chromosphere and corona. The star is extraordinarily information-rich in these dimensions. The brightness is the information, but that same brightness, when you are trying to ask not about the star itself, but about the environment around the star, the planetary companions, the dust structures, the small bodies, becomes the enemy. It is not merely neutral background, it is active interference. The photons that carry the stellar information are the same photons that drown out the planetary signal. You cannot have one without the other. The information density that makes Alpha Centauri A such a precisely measured star is exactly what makes its planetary neighborhood so hard to interrogate. This is a genuinely new scientific problem in the history of planetary science. For most of the history of exoplanet research, the challenge has been one of sensitivity building instruments, sensitive enough to detect the tiny signals that distant planets produce in transit photometry, in radial velocity spectroscopy, in direct imaging contrast curves. The solution has generally been to build bigger and more sensitive instruments, and this approach has worked spectacularly well. Webb's sensitivity to faint thermal infrared sources is the product of a decades-long engineering effort to push sensitivity further and further, and it has enabled the detection of things that were previously undetectable. But for nearby bright stars like Alpha Centauri A, sensitivity in the simple sense of detecting faint signals is not the limiting factor. The signal from a Saturn mass gas giant at 2 astronomical units from Alpha Centauri A is not, by the standards of what Webb can detect at the relevant wavelengths, at the edge of detectability in terms of absolute flux. The limiting factor is contrast, the ratio between the planet signal and the stellar background noise that the planet sits on top of. And contrast is a different kind of problem from sensitivity, one that does not have a straightforward solution of simply building a bigger mirror or a more sensitive detector. Improving contrast requires either suppressing the stellar background more effectively, deeper coronagraphic rejection, better wavefront control, more precise reference star subtraction, or finding observational regimes where the contrast ratio is more favorable. The MIRI F1550C band was chosen partly for its more favorable contrast ratio compared to shorter wavelengths, but even here, 10,000 to 1 is a profound challenge. Future space telescopes specifically designed for high-contrast direct imaging of nearby sun-like stars, mission concepts like the Habitable Worlds Observatory currently being developed as the next major flagship telescope. After Webb are being engineered around the problem of contrast at nearby stars, with coronagraph designs optimized for stellar suppression depths of billions, to one at the angular separations relevant to Earth-sized planets. These missions are still a decade or more away from launch. In the meantime, Webb represents the closest thing we have to an instrument capable of addressing the contrast problem at the nearest stellar systems. And Webb has shown us, through the Alpha Centauri A campaign, exactly where its limits are. It can detect a Saturn mass gas giant at 2 astronomical units if the planet is at a favorable orbital phase with adequate projected separation from the star. It cannot reliably detect the same planet when that separation drops below its inner working angle. It cannot yet follow up a detection quickly enough to characterize the orbital motion before the geometry changes. It is performing heroically at the edge of its design envelope, and the result, a tantalizing single epoch detection, followed by ambiguous non-detections, is an honest portrait of what heroic performance at the edge of design capability looks like. Not triumphant confirmation, not clean failure, a partial answer demanding more. What makes this situation philosophically interesting, and it is appropriate to bring the philosophical dimension in now, in this final part of the story, is what it says about the relationship between observation and understanding when the object of study is something as fundamental as a nearby stellar system. We tend to think of understanding as a property of knowledge about a thing, as if the system itself either is or is not understood, and the question is merely whether we have accumulated enough information to cross some threshold of knowledge. But the Alpha Centauri A situation reveals that understanding is also a function of the tools we bring to the question. For 2 centuries, the system was understood in the dimensions that spectroscopy and astrometry and orbital mechanics could address. It was a well-characterized stellar binary with a known distance and a known age and a known chemical composition. That was true understanding within its domain. But it was also fundamentally incomplete, because the planetary dimension, the question of what the system contains beyond its 2 main stars, was inaccessible to those tools. When Webb arrived and opened the thermal infrared coronagraphic window, a new dimension of the system came into view. And what came into view was not reassuring. It was not a clean, empty system that we can safely say harbors nothing. It was a complex, ambiguous, partially glimpsed structure that suggests the system has more going on in its inner regions than the previous 2 centuries of observation had been able to reveal. The first look, with a genuinely capable instrument, did not produce a clear answer. It produced a richer question. This pattern, where a more powerful tool makes a system harder to characterize rather than easier, at least initially, is a recurring motif in the history of science that tends to get smoothed over in retrospective accounts. When Galileo first turned a telescope on Jupiter and saw 4 points of light orbiting it, the solar system did not immediately become simpler. It became more complicated. Here were new objects with new orbital mechanics, disrupting the model of Earth as the center around which everything moved. When astronomers first resolved individual stars in Andromeda and realized it was a separate galaxy rather than a nebula within our own, the universe did not become simpler. It became vastly more complex. Here was a structure of incomprehensible scale, containing hundreds of billions of stars, and our own galaxy was just one of uncountably many like it. When Webb looked at the first few fields of early galaxies and found mature, massive structures existing just 600 million years after the Big Bang, the standard model of galaxy formation did not become simpler. It became challenged. Here were galaxies too massive, too evolved, too structured for the timescales the models predicted. The Alpha Centauri A observation follows this same pattern at a different scale and with a different subject. The nearest Sun-like stellar system, examined by the most capable coronagraphic instrument yet deployed, does not reveal a clean, empty, well-understood inner environment. It reveals a possible gas giant in an eccentric orbit that disappears and reappears on the schedule of a complex orbital geometry, requiring millions of simulated trajectories to partially constrain, remaining unconfirmed after the full scope of currently available follow-up observations. The system got harder to describe in one sentence, not easier when Webb looked at it seriously. That is what scientific progress feels like from inside the process, as opposed to from outside in retrospect. The implications of this for the broader program of nearby stellar system characterization are significant. If Alpha Centauri A, the nearest Sun-like star, the most carefully selected target, the subject of the most carefully engineered observation in the coronagraphic program, produces this level of ambiguity from its first serious direct imaging campaign, what should we expect from the next several nearest Sun-like stars? The answer is almost certainly more complexity, more ambiguity, more partial answers demanding more follow-up. The nearby stellar universe, seen through the right instrument for the first time, is likely to reveal layer after layer of previously invisible structure, planets, debris disks, dust distributions, companion objects that have been hidden not by their faintness in absolute terms, but by the contrast problem that brightness and proximity combine to create. This means the coming decades of direct imaging astronomy will be characterized not by a series of clean confirmations. Here is the planet, here is its spectrum, here is its composition, but by a long process of partial detections, follow-up campaigns, orbital model refinement, technical development, and gradual accumulation of certainty. The nearby stellar systems will not give up their planetary inventories easily, not because the planets are rare or the instruments inadequate, but because the observational geometry of closeness creates its own specific category of difficulty that requires specific solutions. Solutions that are being developed right now in real time through exactly the kind of campaign that Webb is conducting at Alpha Centauri A. There is something important in the way the nearest Sun-like stellar system in the sky has received James Webb's most demanding coronagraphic observations and responded with something that is neither a clean confirmation nor a clean refutation. It is as if the system has been waiting across all the decades of stellar measurement that characterized its mass and temperature and age with such precision for someone to ask the right question, and when the right question was finally asked with the right instrument, it answered, not with a simple yes or no, but with a qualified maybe, that demands to be taken seriously precisely because of how carefully it was extracted from such difficult data. This is not anthropomorphism. Stars do not wait or answer in any intentional sense. But scientifically, the experience of asking a system a question it was previously impossible to ask, and getting an answer that turns out to be more complicated than the question seemed to warrant, has a certain quality to it that deserves acknowledgement. The quality is this: proximity does not guarantee familiarity, and familiarity does not guarantee understanding. These are not the same thing, And the history of science is full of examples where conflating them led to confident claims about the state of knowledge that turned out to be premature. We knew Alpha Centauri A well, in the dimensions that 2 centuries of careful stellar science could address. We did not know it well in the dimension that matters most for the question of whether it is cosmically alone or cosmically accompanied. That dimension opened up in August 2024, and what it showed was not a solved system, but a system still holding its deepest structure back, yielding it gradually and on its own terms, demanding better instruments and better strategies and more telescope time before it will show its hand fully. The deeper truth this points toward is about the nature of the nearby universe itself. We have tended to picture the stars nearest to us as the ones we understand best, and as the ones most likely to have given up their secrets first. The stars, far away, the distant galaxies, the high redshift objects, the systems whose light has traveled for billions of years to reach us, those are the unknown ones, the mysterious ones, the frontier of astronomical ignorance. The nearby stars are supposed to be the known ones, the characterized ones, the baseline against which we measure everything else. The Alpha Centauri, a planet candidate, complicates that picture in an irreversible way. Once you know that the nearest Sun-like stellar system has been hiding possible planetary scale structure for all the decades it has been studied, you cannot unlearn that fact about the category of things it belongs to. You have to recalibrate your expectations about all the nearby systems. Tau Ceti at 12 light-years, Epsilon Eridani at 10.5 light-years, Eta Cassiopeiae at 19 light-years, 47, Ursae Majoris at 46 light-years. These are all Sun-like or near-Sun-like stars that have been characterized in their stellar parameters, mass, temperature, age, composition with high precision. They all have planet candidates from radial velocity data, some stronger than others, none as rigorously characterized as we would want. If Alpha Centauri A, the closest and best studied of the Sun-like stars, turns out to have a gas giant in its habitable zone that took until 2024 to even tentatively detect, what are the planetary architectures of these other nearby systems actually like? How many giant planets, how many debris structures, how many dynamically active inner system features do they contain that our current instruments have not yet been able to reveal? The answer is almost certainly more than we think. The planetary inventories of the nearest Sun-like stars are, by the standard of what direct imaging with adequate contrast performance can reveal, almost entirely unknown. The radial velocity campaigns have found candidates at various orbital separations subject to the limitations of that technique when applied to binary or multi-star environments. But direct imaging, which would actually show us where the planets are and what they look like in the thermal infrared, has barely scratched the surface of the nearest stellar systems. Alpha Centauri A is the first serious attempt, and the first serious attempt produced something that is either a real planet or a highly constraining observational mystery. Either outcome is telling us that the nearby stellar universe is richer and more complex than the pre-Webb picture had allowed us to see. There is also the question of what the specific properties of the Alpha Centauri A candidate, if it is real, tell us about planet formation in binary stellar systems, a question that has been theoretically active for decades, but observationally starved of data at the most relevant scales. The theoretical models of planet formation in binaries make predictions about which orbital separations are stable, which architectures are possible, and how the binary companion's gravitational influence shapes the dynamical evolution of the inner planetary system over long timescales. A confirmed gas giant with the orbital parameters suggested by the current data, moderately eccentric, inclined relative to the binary plane, at a separation consistent with the inner stable zone predicted by the dynamical models, would be the most important single data point ever obtained for testing these predictions at the class of systems most relevant to the question of whether Sun-like binaries host potentially habitable worlds. The majority of Sun-like stars in the solar neighborhood are in binary or multiple star systems. This is not a marginal fraction. Rough estimates suggest that somewhere between 40 and 50% of Sun-like stars have stellar companions. If binary systems cannot form or maintain planets in their habitable zones, then the prospects for planetary habitability around a large fraction of the nearest Sun-like stars are significantly reduced. If binary systems can form and maintain such planets, as the theoretical models suggest, is at least possible for certain binary separations and mass ratios, then the prospects open up considerably. The Alpha Centauri system, with its well-characterized binary parameters and its proximity that makes it the most accessible test case for these questions, sits at the center of this issue. A confirmed planet there would not just answer the question of whether Alpha Centauri A has a world worth caring about. It would answer a question about the viability of planetary systems in a class of stellar environments that contains a significant fraction of all the Sun-like stars within reach of future exploration. None of this, of course, depends on the candidate being real. The scientific significance of the question is the same regardless of whether S1 eventually confirms as a planet or is eventually identified as something else. But the candidate's existence as an observation demanding explanation, as a data point anchoring orbital models, as an impetus for follow-up campaigns that are already being planned, has pushed the question to the front of the field's agenda in a way that no theoretical argument alone could have managed. There is a specific power that a robust observational detection carries, even when it is a candidate detection, that changes the terms of a scientific conversation. Before August 2024, the question of whether Alpha Centauri A has planets was a theoretical and motivational question, something to design future instruments for, something to hope for, something to estimate probabilities about. After August 2024, it is an observational question, something that has produced a specific signal at a specific location that must be explained. The fact that explaining it fully requires more observations, that the current data cannot definitively resolve the ambiguity, that the system has kept the answer partially hidden, even under Webb's gaze. This is not a failure of the scientific program. It is a precise description of where the scientific frontier actually lies. The frontier is not somewhere comfortably far away, in the early universe, or in distant stellar populations, or in high-energy phenomena at vast remove. The frontier is 4.37 light-years away, in the nearest Sun-like stellar system in the sky, where the most powerful space observatory ever built has looked and found something that is either a planet or a mystery, and where the work of resolving that ambiguity will define a significant portion of observational astronomy in the years ahead. The story of Alpha Centauri, told in this way, is ultimately a story about where the edges of understanding actually are, and the genuinely unsettling discovery that those edges do not respect our intuitions about scale. We assumed the edge was far. We assumed that the nearest things were the best known, that centuries of observation had given us a solid grasp of what was there, that when Webb looked at Alpha Centauri, it would either confirm a planet we had missed or cleanly rule one out. Instead, Webb looked and found ambiguity at a depth that 2 centuries of previous observation could not even have framed. The edge of understanding, it turns out, was always right there, not at cosmological distances, not in the early universe, at 4 light years and change, in a star system we named and catalogued and measured with pride and thought we knew. The nearest sun-like stellar system in the sky is not a solved address. James Webb Space Telescope looked directly at it and found something that may be a world, and that is not less disturbing than finding nothing. It is more disturbing because a world that appears and disappears, that hides in its star's glare and resurfaces only when the geometry cooperates, that requires a disappearing planet protocol and millions of orbital simulations just to begin to characterize, is a world that belongs to a system that is still capable of surprising us. A system that has spent 4 light years of distance earning a reputation for familiarity, only to reveal, under genuine scrutiny, that familiarity and understanding were never the same thing. That the nearest bright point in the southern sky is not a known quantity, but an ongoing question. That even the closest major sun-like neighbor, the one we named and measured and aimed our dreams at for 200 years, is still withholding something, still holding its most consequential truths, just far enough from our instruments to remain, for now, just beyond complete reach. Rest now, explorer, the nearest sun still burns with secrets. Your instruments are only beginning to learn how to ask for.